Okay, good evening. Welcome to the next in our series of methods mathematics. I'm not sure if our host is actually there at the moment. Brian, are you there?
He is. Hey, how you doing?
Hi, Brian. Thank you. I thought I might just take over there. I wasn't sure. Thank you, Brian.
My telephone, I just did a beautiful introduction. And, all at this point, and then looked at my phone and saw still on mute. So,
good evening, Brian. I'll pass back to you.
Good evening indeed. Good evening indeed. Well, had people been here in my office, they would have heard me welcome and talk about how important this afternoon's topic is, discrete and continuous random variables and the normal distribution, which is a step away from the standard calculus and algebra topics that comprises most of the course. There is, of course, calculus and algebra in this as well, but particularly looking at the probabilities involved. It's a topic that I know students often have difficulty with, so pay attention. This is an important session. Just a couple of housekeeping matters. Remember, if you do have audio difficulties through your computer, to phone in 1800 708 203 and quote the event number 825 673 356, and that information is also in the chat window. And the other one, of course, as your instructor talks you through the various problems, have your calculator at the ready. Please work through them with him, and please also type in the answers or any questions you may have into the Q&A panel when he asks you to do this. Please direct your questions, if you have them, to all panelists. And so, without further ado, I have already done this introduction once this afternoon, but you just didn't hear it because my phone was muted. Can I introduce you to, please, the man who puts the step into Stephen, the jewel into Julian, and the into Mandurah Catholic College? It is indeed Mr. Stephen Julian of Mandurah Catholic College.
Thank you very much,
Stephen.
Brian. And I think we should already have my screen up and ready to go, I think. So we'll get straight into it. And good evening, everyone, and thank you for that wonderful second introduction, Brian. And for the second time, people are actually hearing my voice for the night, probably mainly for the first time, hopefully. Anyway, we'll get straight into it. Just also, I do apologise. We're having a great night here. I've just had my next-door neighbour start up a bandsaw, so if you hear any noises in the background, it's not me trying to do some random experiment ready for normal distributions. It's, my neighbour timing things absolutely perfectly for me, so bear with me if it gets a little bit loud in here tonight. We're having a great one. Anyway, straight into it. Tonight we are looking, as Brian mentioned, the discrete and continuous random variables and the normal distribution. We've got 8 questions I'm going to try to get through with you tonight, so we'll just see how things pan out. And as Brian mentioned, it is one of those topics that, unlike calculus, where often you do get worded problems, often with calculus it's also just differentiate this or find this. With the probability area, I know with my own students, and it's great to see a number of them on here again tonight, is that it's just the wording, trying to nut through what the question's asking, what kind of distribution it is, and knowing when to do what. So hopefully tonight we'll be able to answer a few of those questions and clear up a few concerns that you might have. So anyway, let's get into it. So our first slide, I just wanted, as I've done for the previous weeks, just to talk about a few things that can be done with our calculator. The first screen I don't really want to spend too much time on because we'll get back to that next week on sampling, but I guess the two main ones that might be of use for us within this work is the binomial and the normal random generator. So I'm just going to show you here, if we go into a new document screen, and we'll make a calculator. And we're going to just quickly see the syntax that we could be using for this particular situation. So if I go into menu, and we're doing probability, random, binomial. Now, as I've mentioned, and as the wonderful Hayley said right back at the start of the very first session, if you're not sure about the syntax that you need for these brackets, just go into the home key. Oh, now we're having a little bit of an issue there with that tonight. So, sorry. Normally you can go into the catalogue key and we get a nice list of things happening. Now, I've had a little bit of an issue a couple of times with the Macintosh with this particular thing. I'm not going to reset it. Normally what would happen is if I reset the whole software, they'll come up, but I won't do that for you people tonight. So let's just go back into probability, random, binomial. I'll try it one more time. No, it's not liking it on this tonight, so I'll just escape out of that. And the syntax for it is normally, sorry about this, people.
So just through the main menus, yep.
Yep, so through the main menus, if we go into random, and if you go into binomial, and if you want to get something that's generated, in our normal syntax we have, say, trials, so it might be 10 trials. Our probability of success is 0.2, and we might want to find out we might want 5 samples of that. So 10 for trials, so it might be 10 outcomes, whatever, 0.2 in terms of the probability of success, and we want to generate 5 numbers of those. If I press enter, and straight away you'll notice towards the lower end of our 10 successes, or out of our 10 possibilities, 2, 3, 3, 1, 4. That can actually be used in tables and can be done in other ways, which again we'll do in sampling next week. The other one I just wanted to quickly touch on was the random normal. Now again, as per usual, we've got our mean, so we could do a mean of 10, standard deviation, say, of 2, and again we might want to generate 5 numbers. Now, one thing I'd be thinking at this stage with students, if I was discussing this with my own group, is obviously with the binomial, we're talking about generating a number of successes here, and that's why it has to be between 0 and 10. You'll notice with the normal distribution, if I just scroll across, we are hovering around that 10 mark. So, again, reasonably well within 2 standard deviations as well. So, 8, 11... we've got a lot of nice little decimal numbers going on there. Again, next week we'll touch more on that from a sampling point of view, but it could come up within any of our probability questions as well. Okay, the other part, and some of these other things, by the way, the seed and sample, again, I'll touch on next week. The other things that could be useful for us in our probability distributions are the normal PDF, normal CDF. So again, PDF, a lot of students have to remind themselves that, yes, we're talking about an exact value there. If it's a CDF, we're talking about a cumulative distribution function, so where it might be a series of values or it might be between limits. The inverse normal, the binomial PDF, and the binomial CDF. Excuse me. Again, most of those things we'll cover tonight, so just make sure that you're aware that in menu, under 5, if we go into 5 again, distributions, we can find all our different things under there, such as the normal PDF, normal CDF, inverse normal. So they'll be where we find those tonight. Okay, moving on to our first question. Now, in our first question tonight, I've tried to break this up into our discrete random variables and taking it all the way through to our continuous and then finally into our normal. So pretty much each question covers a certain area. So this first question that we have says the probability density function for a discrete random variable x is given by probability of x equals little x. And again, this is a discrete variable, so obviously we can only have exact values and then 0 for otherwise. Find the value of k. So I'm going to give you a couple of opportunities tonight to have a go at each of these questions. This is going to be the first one. I want people to see if they can find k within their own means, whether it's pen and paper, whether it's using calculator, how you feel that you would like to do it. So I'll give you about 30 seconds to see if you can find the equivalent, the correct value of k. And I'll let Brian keep me informed on how those answers are coming through from our panellists and our participants.
I'm watching. I'm thinking on the idea that does all probabilities add up to 1 or thereabouts?
I think that might be the thing we need to think about here. And we should be thinking about a summation situation, which I'll show you in a moment on our calculator. Okay.
I know that there's a fairly powerful brains trust online here. So we might see what they've got done. And they've come in with a value, yes.
What's our first value, Brian?
How about 1 over 15?
That sounds pretty good. Let's give everyone else maybe another 10 seconds to see if they can come up with the same answer. Any other 1 over 15s coming through, Brian?
You'd think they'd all be jumping on that now I said it.
I think so, yeah. And knowing a few of the students of my own sitting there, they're very good at agreeing with each other, sometimes hopefully for the right reasons, and with me as well. So let's have a look and see how I would do this using the calculator. So again, we could use the idea that Brian mentioned, that obviously being a PDF, a probability density function, our sum of these values should be 1. Again, it is a discrete situation, so we can't deal with area here. We've actually got to look at individual values. So one way we could do this is go into menu, and we could go into calculus, and under calculus number 5 is sum. So if we did that, now our values here, we're talking about x being between 1 and 5, and actually, sorry, I should have put a solve in front of all that, would be a good idea. So solve, and then we're going to look at k multiplied by 6 take x, whoops, 6 take x, and we're going to say that that sum is going to equal 1. Okay, and again, I think that should be just outside my bracket. Okay, so equals 1, and then we're solving for k. So saying that all our values sum up to 1 for k, let's see, drum roll, and we get k equals 1 over 15. So that very clever person, and hopefully all the other participants, were also able to get that value. Now, the next part of the question says construct a table showing the PDF for x. So with this next step, what I'd suggest is we Control-I and go in and make up a table. So we're going to look at a list and spreadsheet. What I'd now like to see, and again, this question, we're actually going to try to create some connections down towards the end with our various linear transformations happening with this question. So I'm going to go up to the top and actually call that first column x. I'm then going to, I want to create the numbers 1 through to 5. Now, this is just a little trick for anyone who hasn't seen it. I know that 1 to 5 isn't a huge list, but if we just type in the numbers 1 and 2, if I then push Shift and then down and copy that, and then if I go to Menu, Data, and Fill, if we go down to our 5th number, press Enter, and what you'll see is it's actually generated that sequence. So it's actually picked up that the numbers are going up by 1. So that's really a quick way, particularly if you have a large number of numbers that you want to generate. It can work for pretty much all arithmetic sequences, so it works really, really nicely. Okay, in the next column, what we want to do is we're setting up a table, so our PDF I'm going to call P. And then in this cell, our formula cell, I'm going to press equals, and we're going to use our K value, which was 1 on 15. We could use the fraction template if we wanted to, times by, bracket, 6 take. Now, I want to use the values that I've just created in that first column, so the x values. So if I go to the var key, which is just above your 9, you'll notice that there's the x is one of the options we have under there. So if we click on that, you'll actually see it comes out in bold with a little apostrophe before it. It's saying, yes, I recognise that that's something we've already created up before. So if we now press Enter, and because I've got mine in, and it was something I was going to mention at the start, in auto, it's actually coming up with the answers in fraction form. If you're getting it as decimals, that's fine. Again, it depends on what the question's saying in the exam. Make sure that if they're talking about exact, that that's what you give them. So things like fractions, thirds, square root, in form with square roots. If it says that once to a certain amount of decimal places, that's exactly what they need and want. So in this case, we've got 1 over 3. If you haven't got your calculator set up correctly, we can go up into Doc, Settings and Status, and go into the Document Settings. And just under Calculation Mode, you'll notice I've got here Auto, so that the calculator can try to be a little bit smart about what it picks as your answer. If it feels it needs to be a fraction, it'll give it really nicely for you. I'm just going to go OK, although it won't change anything on my screen. So we'll notice here now that we've got our construct a table showing our values. We've actually got those nicely ready to type in or write down on our exam. Okay, the next thing it talks about is finding the probability of x is greater than or equal to 2, given x is less than 4. I might skip over that one because we're going to do some givens a little bit later. Hopefully people are aware that we're looking at the intersection between those two statements as our top part of our fraction over the given part, which would be x is less than 4. So our intersection would be 2 is less than or equal to x, which is less than 4. Because it's a discrete situation, we could also treat that as being x is less than or equal to 3. Okay, so again, we can either include the 3 and make that our higher limit, or if we're going to use 4, it would be less than 4. I'm going to jump into the next part, which is finding the expected value and the variance of x, so our mean and our variance. Excuse me. To do that, we're going to go into Menu, Statistics, and number 1, Stat Calculation. One variable statistics, even though we've got 2 columns, we're treating our second column as being like our frequency. Our first column is our actual score. So we're treating it as one variable statistic, one list of numbers, even though, again, we do have 2. The second list is being treated as a frequency, so okay. Now, in this screen, if you push right, you should get X as being your X1 list. If we go down to the next one and pick P as our frequency list, and then I'm going to go down to the bottom and just change that to C, just so we can keep everything up next to each other. That will give us our first column results. If we do that, now in this case you'll see here that because I've gone into auto, it's actually picked up, excuse me, that some of these answers are best as decimals. Again, depending on how you set your calculator up with whether it's in exact or in approximate mode, again, you'll have different options that will come up with your results. Excuse me, sorry about that. So, in terms of our mean here, our expected value, we should get 2.333 recurring, or 2 1/3 as our value. So that's our answer for Part D expected. If we come down to our standard deviation, and we use the sigma x for this one, you should find that we are getting an answer of 1.24721. Okay, so in terms of our final result. In terms of using those values now, now it's interesting here that it's picking up something has gone, saying that there's only one number, one minimum. Okay, I might just see what's happened there. We've got the right mean. The standard deviation has come out a little bit different to how I expected. Probability, no, that all looks pretty good to me. So we might just jump on to the next part. Actually, I might just, regenerate that. For some reason, it's not liking... because of the relative frequency, of course. Thank you. Just got a message coming through. The relative frequency is giving me one. But again, the standard deviation should be all fine for us with what we're actually getting. Sorry about that. I've just mental blank there for a minute. So let's go on to the next part. Let's now look at what would happen if we changed y being 3x. So we're now doing a linear transformation with our function. So I'm going to come over into now our E column, and we're going to change that into, I'm going to make it x2. So it's going to be the second of the x values that we're going to work with. We could call it y. I'm just going to keep a record of knowing which x I'm trying to work out. So x2. I want this column to be 3 times the value that we just typed in the first column. So again, we can do 3 times var. If we push the var button, what we should find is we get a whole list of options. The one I want is right down the bottom, which was the x value from our original list. If we press enter there, what you should find is that each of the numbers in our first list has been actually now multiplied by 3. Now, that's going to lead to my next question, which is what do we expect that to do to our expected value and our variance? So again, I'll leave that open for Brian just to take a couple of quick responses. What is multiplying the x value going to do to our expected value and to our variance? So again, Brian, if you could just keep an eye on the other helpers, keep an eye on the chat site for me.
Watching that, yep. Meanwhile, Stephen, I was just typing in a response to a question: how many decimal places or sig figs should be used in the WACE exams. My answer to that is generally look at the wording in the question. So the question should either specify exact, in which case it needs to be, or it should specify the number of decimal places. And if it specifies a number of decimal places, make sure you round correctly as well.
Yeah. And I agree, 100%, Brian. If it's not mentioned, generally we would leave it in the exact form. What I have said to my own students, again, particularly if they feel that it's something that they're going to be working with decimals, or it's made clear later in the question that they're going to use decimals, I often suggest either 4 decimal places with probability or 4 significant figures if it's something that's starting with a few zeros at the start. But again, most importantly, and as my students were finding today, it would be a case that we'd be looking at exact values if not stated otherwise. So exactly right, Brian. Do we have any answers coming through?
I'll just get back onto that. We have.
Yep, I think I saw one flash up on the screen, but I'll leave you to have a look at that.
Increase the standard deviation and expected value.
Yep, by how much, so I guess is the question, but we won't wait any longer for that so that we can get on to our next question. So what I'm going to do is just quickly generate our values and find out what's going to happen in our next column. So I'm actually going to use the F column as my next result column, and we're going to go through the same process again. So menu, statistics, 1 stat calculation, 1 variable statistic, and OK. Again, we're going to use this time the X2 value. Our frequency is still going to be the same probability because, again, those values, even though it's a linear transformation, still have the same probabilities of occurring for each of the things. And I'm going to come down to the bottom and change that into F as being my first result. If I do that, what we should find is that our mean has now become 7. Before it was 2 1/3. So yes, that's a multiplication. It's an increase. So I agree with whoever made the comment about increase. But you should notice that we've actually multiplied it by the 3. If we come down to the lower part, and this is where I'm interested in something that's actually happened here with my results. Again, we're into variance and we want standard deviation. What we should find here is our standard deviation has been multiplied by 3. But what we might want to do is, because the question asks for variance and our standard deviation has been multiplied by 3, if I copy that, so Control C, come back to the previous page, Control V it, and then square it. And what we should find is that we get 9 times the value that we had in the first part, which was 1 point something or other. But we should find that we actually get 9 times that original value. And that leads into the idea of whatever the A value, the coefficient of the X when we do the linear transformation, if we square that value and then multiply it by our previous variance, we should get the right answer. Okay, let's do the last one of these. So we're going into 1.2, and I'll now call this X3. We're going to go through the same process again. So this time we're going to have equals. We're going to times our original X value by 2. So again, using the var key, we can pull up X from our original values, and then we're going to add 3. If I press enter, what we should find is our original numbers of 1, 2, 3, 4, and 5 have become 5, 7, 9, 11, and 13. So multiplied by 2, and then we're adding 3. Let's now look at what happens there. Hopefully students are aware now that because we're also adding as well as doing the multiplication, that both those values are going to affect our expected value. And for our variance, the plus 3 part shouldn't have any impact, but we should have some kind of multiplication occurring for that. So into our menu, statistics, stat calc, number 1, OK. Now, whoops, I should have a look which list I wanted to save that into. It's actually going to be the I list. So OK. Now, again, we're going to use this time the X3 values. Our frequency is going to be our probabilities, and I want to save that into the I column. If I go OK, what we should find here is we had our original value of 2.33 or 2 1/3. Our new mean has moved up to 7 2/3. So we've multiplied by 2 and added 3. And our variance down here, or our standard deviation, looks like it's 2 times the original value. Again, I'm just going to confirm that we actually are really timesing that by 4, by Control C, coming back to my original screen, Control V, and then we're going to square that, and we should find that that's actually 4 times the value that we had for the original variance on the previous screen. So that's the first use, so looking at the idea of our discrete random variables. Our next question that we're going to move on to is the probability density function for a discrete uniform variable is given by P of x equals 1 on n, for x equals 1 through to n. We first of all want to generalise this situation, so this is going to be a uniform distribution. We want to generalise the E of x and var of x for this PDF, and hence or otherwise find the expected value and the variance for this discrete uniform variable, given that we're actually using 1 on 6. So in other words, n becomes the 6 rather than just a standardisation. So going back to our calculator. Now the results of this is a little bit more about just generalising and coming up with what we expect as being the value, the correct formulas for these. So sometimes in an exam it might ask you to prove or show that you agree with a particular rule. So in this one here, because we've got a discrete uniform distribution, we want to find the expected value. Because it's discrete, we're again going to start with the fact it's a summation rather than an integral. We're going to go from x. Now, this is a good lesson for the novice to learn, because I haven't gone into a new problem, which is what I did during my practice. You notice my x came bold. So what I'd suggest here is, because I'm going to try to keep a bit of an ongoing documentation here, something that you might be able to save to your own calculator, I'm going to go into Doc, Insert, and we're going to put in a new problem, which we've talked about in previous weeks. This way, all my variables are reset to just being variables I can use, and we can go right back to using x's as if they're x's rather than worrying about clashing with other things that we might have done previously. So now I've got problem 2 up the top. I'm going to go into Menu. We're going to go into Calculus and Sum. We're going to make that x equals 1. Now, because we don't know our upper value, I'm going to put n as our upper limit. So this is, again, showing the power of these calculators, that they can actually generalise things really, really nicely for us. Now, because we're trying to find the expected value, our expected value is normally the x value multiplied by the probability. So Control and divide, we get our template, 1 over n. Now, for anyone who's already thought through this process, what we should find is we get this result, n plus 1 on 2. Now, this shouldn't surprise us, because we should know that if we were using a normal fair die, that our n value would be 6, which is the problem I'm about to look at. 6 plus 1 is 7. 7 divided by 2 is 3.5 or 3.5, which is what we'd expect as the expected value of a fair die. So this rule does seem to be working really nicely. The next part, the variance part. So for the variance, what we normally do is, again, we do Menu. Now, rather than going through the whole thing again, I'm just going to cut and paste that, or just copy that. So go up and highlight it, press Enter, go across to our x, and let's make it x squared. So part of our rule here is we've got the e of x squared, take e of x all squared. So we're substituting x squared into our expected value, and then we're taking the expected value that we just got, but we're actually going to square it. If I press Enter there, you get this statement, which is not particularly useful for us yet, but what we do need to do is the other part, which is expand. So Menu, Algebra, which we talked about last week, expand. I want to expand that statement, take the statement up the top we just got. So this is now our e of x squared, take our e of x all squared. If we press Enter, we get that as our rule, which is basically n squared take 1 all on 12, which is our rule that we can use for the variance of these kind of situations for discrete uniform distributions. We might now want to move on and find out what happens if n is 6. So a couple of ways we can do that. We could go through and just type in the rule, but if I want to use what we've just got, I'm going to highlight and copy the n plus 1 on 2. Given, so Control equals, and our given sign, n equals 6, and if I press Enter, there's our 3.5 or 7 on 2. Same thing for our variance. If I copy and highlight that, Control, given, n equals 6, and we get that as an answer. Now, that's our variance for a die. So if I actually go Control, Enter, and change that into a decimal. Now, if we actually looked at that and said, okay, well, what did we get previously for the variance, standard deviation of a normal die? I'm just going to square root the variance. And we get approximately 1.71, which, again, hopefully with a lot of practice that you should have had this year on these kind of questions, the two values that you should be very familiar with are the expected value and the standard deviation of a die, and that just confirms that those two values are both working in that situation. So a nice little example there of that. Okay, moving on to the next one. Sorry, Brian, you...
I'm just saying, very, very neat way of doing it. Quite clever. I like it.
Yeah, so nice little way of proving that actually all works and gives you the values. Okay, the next screen I'm going to come back to later, just depending on time. In terms of binomial distributions, most students by this stage of the course should be okay with entering most of these things into their calculator. I guess the one thing I will highlight here is just make sure that if it's x is less than 9, that we do remember that this is a discrete distribution. So because it's a discrete distribution, hello, are we still there, Brian?
Yep, it's all happening.
Yep. That's all right. I think someone was trying to come over my line, so that's all right. Just heard a funny sound in the background there. So, yeah, getting back to what I was saying, because x is less than 9, because it's a discrete situation when we're talking binomial, you should use x is less than or equal to 8. So I might just look at that one on our calculator, but I won't necessarily go through all the rest of them. So on our calculator, because we're now looking at a binomial, I'm actually going to set this up as being document 3. So insert problem 3, just again to keep things nice and separated for the students. We're going to go into calculator. We're going to go into menu and probability. And then because we're looking at a distribution, number 5, now right down at the bottom, we have D and E. Now, if I just scroll down to that. Now, because in part B, we're actually after a range of values, we're going to look at our CDF, a cumulative distribution function. We've got our N value. Now, in this case, in the question, it was 30. Our probability of success was 0.65. Our lower boundary, well, because we're talking about successes, 0 would be our lowest boundary here. We're less than 9. So that means we're not including 9, but because it's discrete, we have to have an exact value. So 0 and 8 would be our lower and upper boundaries. If we go OK, we get a fairly low probability for that one, but because we're thinking 0.65 is our success rate, and we're heading down towards the lower part of our distribution there, we would expect that those probabilities would start getting reasonably low in that situation. The other one I was just going to quickly touch on while I'm in that question is find the mean value and most likely value. Well, for the mean value, we should be aware that to find the mean of a binomial distribution, we're just going to go our n times our p. So in this case, it would be 0.65, which is our p, times by our n, and we get 30. That's our expected mean value, but then the most likely value of x. Now, students will sit at this stage and go, well, is it going to be 19 or is it going to be 20? I'm not really sure whether I should go above or below that value for my most expected. Is it symmetrical? But again, because it's a discrete situation, that value is somewhere in between. So what should I go for as being my most likely value of x? Well, this is where we can actually use a table. Control I. And we can look at our listen spreadsheet. At the top, because we have started a new document, again, I'm going to make that X. And at the top of the next one, I'm going to treat that as being our probabilities or our actual outcomes. In our first column, again, I want to make a list, so I want to do numbers 1 and 2. Shift that, so we actually highlight the 2, so shift and down. Menu, data, and fill. If we just quickly go down to, and again, another little learning error there, not 1 and 2, we should have 0, shouldn't we, Brian?
Yeah.
Then I'll just Control Z and undo that. We should actually be at 0 and 1. Again, highlight that. Menu, data, and fill. Now we're actually going to have to go down to 31 rather than 30 because we want to get all the way to 30 as our options, and you'll notice there 0, down to 30 in terms of our trials or our outcomes for that situation. Now, into the next part, so our equals part. Now, rather than having to generate them individually, we can use our formula cell and push equals. We're going to do a binomial, so into into statistics and distributions. We're going to come down to binomial PDF because we want to look at each individual outcome. Number of trials is 30. Our probability of success is 0.65. And the value that we want to put here is whatever's coming up in the first column. So again, if we push right and the apostrophe X and then down to OK, press Enter. And what we should find is we've generated all the probabilities for all our different outcomes. So looking down here, e to the negative 14 or 10 to the power of negative 14, really small numbers, really small numbers. If we scroll through, we eventually get to a point where we should find there's a little bit of a change going on. And that happens at 21. So notice at 20, we're on 0.14706. On 19, we're on 0.14706. On 20, we're on 0.15021, and then it starts dropping again. So our most likely value would actually be 20, so we'd actually go up a value, not down a value. So again, nice little use of tables, trying to show people different ways of doing things here. So we've had a lot of look at graphs, but we haven't done a lot in the last couple of weeks with tables. A little bit hard with some of the calculus stuff, but a nice little thing there for that kind of question. Okay, moving on to question 4. Now, I will apologise, the PowerPoint that some of you might have accessed earlier today that was put on the share drive actually gave you a hint on one of the answers here, which was the K value. On the original PowerPoint that was sent out, it had X as a continuous random variable with PDF given by f of X equals, now the original one that I picked up about halfway through the day that this was a mistake, and then unfortunately got busy with a side thing I do, which is called teaching, was X squared on 72, which sort of gave the answer a little bit away. But we'll actually have a look now and see why we can get X squared on 72, in other words, the K value of 1 on 72. So I'm going to come back to my calculator. I'm going to set up another new problem. So doc and insert. We're going to put in a problem, and again, we're going to look at calculator here. Now, because this is a PDF, like we did previously with the discrete situation, being continuous, again, we know our probabilities are going to be equal to 1. However, because this is continuous, we should now be thinking, well, it's going to be area. Area, well, what things can we do with functions in area? It's going to be some integration with our function. So we want to find out what this K value is based on the fact that we're now talking area rather than using discrete values. So in our calculator, in menu, come into algebra and solve, because we're going to solve something. Now you should hopefully remember from last week we talked about the shortcut shift and plus, which gives you your template for integration. 0 to 6. Our function that we're working with is K times by X squared. Now I'm just going to move outside of that and put our X for our dx, and then be careful here again, we must push one time to the right to just get outside the integral template, then equals 1, comma K, and what we're hopefully now going to find out is that 1 on 72 is in fact the right answer for K. And again, sorry, but the version that you might have in front of you may have already given that away. We now want to sketch that graph, so we want to come into a graphing screen, Control I. We're going to look at the graphs option, number 2. I'm going to put in the function that we just did, so Control and divide for our template. We have X squared on 72. But what we want to do is we actually want to restrict it between the values of 0 to 6. So in the control equals part, we've got our given sign again. From 0 is less than or equal to X, which is less than or equal to 6. And if I press Enter, we'll get the part of the graph that we're actually after. Now, at the moment, it's not huge for us, so I'm just going to move this label out of our way altogether. So I might put it down in the corner there. We're going to change our view window. So I'm going to go into Menu, Window Zoom, and I'm going to go for A Zoom Fit. And what we hope we'll get is a nice view of this particular graph. And you'll notice there's our graph. Now, what we could do is there's a heap of things that we could actually do with that. We could confirm it's a PDF by the fact that the area under that graph is going to be 1. So let's try that. Menu, Analyze Graph, and Integral. Remember from last week that we can move the lower boundary, or we can just type in 0 for our lower boundary. It'll go there straight away. We can now type in 1 for our upper boundary, just make sure that it is to the right of our lower boundary. And what we should get is appearing, 0 to 1. Why did I go 1, Brian? That was a silly move.
I was wondering then. We wanted to go.
Yeah, it must be getting to that time of the night, I think. Okay, I'll do that again. Sorry, people.
Thinking of what you're going to get.
Yeah, I've got a very small number that was nothing like what I wanted, and I knew straight away as soon as I pushed it. The students of mine who are on that watching tonight will be used to that occasionally, where it's just a Julian moment. So let's try that again. Let's go 0. And this time we'll go for 6 as our upper boundary. And what we should notice there is we get 1 as our area. Okay, so straight away that confirms that, yes, we have our PDF, and it's a nice illustration of that situation. We could do the same thing for the next couple of parts, so particularly finding the probability of 1 to 4, but I'm going to come back to my calculator display and just do that the traditional way with the integrals. So Menu, Calculus, Integral. We're going from 1 to 4, and then our function, which we've already worked out, is Control, and we're dividing x squared on 72 dx, and that gives us our value for the next one, which is 7 on 24 as an exact value. And again, if we wanted that as a decimal, we could go Control Enter and give it to whatever decimal places that the exam might ask. The next one, rather than retyping the whole thing in, I'm just going to go up and highlight it. Come down to the bottom. Now this time we're talking about being greater than 2, but because it's a continuous variable, we can actually treat it as also equal to, because the probability of that is so negligible, unlike a discrete one where you've got to be very, very careful. Our upper boundary, because it's saying greater than 2, but our higher limit is 6, and if we press Enter, we get 26 on 7. I'm going to jump over Part E. And what I'd like, again, just to get students involved again and the participants involved, I'd like people to now have a think about Part F and see if they can come up with what the M value would be for this next question. So I'll give people about a minute to think about how could we find now the value of M, given that M is our upper boundary and 0.8 is the area that we're trying to find.
So we do it a little bit inside out, are we not?
Yeah, so now we're actually, rather than having the boundaries and going for the area, we've got the area and we're trying to find the boundaries. And again, being a continuous random variable, now, we've had a person come through very, very quickly with 5.57 I saw flash up on the screen. Brian, is that right? Is that what I just saw?
That's what you saw.
That must have been one of the quickest answers I've ever seen. Speedy Gonzalez, I think. That was unbelievable. A very, very, very quick answer come up on that screen. So what I might do there is, since we've already got an answer, the way we can attack this question is, again, from a solve situation. So Menu and Solve. We're going to do an integral. Again, I could have used my Shift and plus. Our lower limit, because it's saying less than or equal to M, which means our lower limit would be 0. We have M as our upper limit. Our function that we're actually working with is still the original function that we've just been working with, so x squared over 72. And we want that whole thing to be equal to 0.8, and we're solving for M. And the answer of 5.57, well done to the person who quickly put that up on the screen. Excellent, and that was, in fact, our right answer. So very, very good. The next part of our steps, again, I might just skip over the given questions. Oh, sorry, that was actually the previous one, but the given question, and we'll just jump to our find the E of X and var of X, because again, these are the kind of questions fairly new to this course, and I think compared to the old previous Western Australian courses, I think it's going to be something that definitely there's either going to be an E of X or var of X of either a discrete or a continuous random variable happening on this exam. So if we are working with a calculator and we're looking at this next idea, to get the continuous expected value, we're going to use our integral. I'm just going to copy it and just quickly change, just to make it so I'm not having to type everything in fresh. We're going to have 0 as our bottom value. 6 is still our highest value. Now, you may remember from earlier in the night, I mentioned that if we're doing the probability, we're multiplying the score by the probability. So in this case, our x squared on 72 is our probability statement. So I'm going to times that by x. I could do that manually and just work out it's x cubed on top, or times it by x. And if I do that correctly, we should get 9 on 2 or 4.5 or 4.5 as our answer, in this case an exact value of 9 on 2. Again, the examiners are going to be happy for you to leave it as improper fractions. In a lot of cases, it's actually more convenient to work with improper fractions in some cases with other parts of the problem. So 9 on 2 is fine. Again, if you were going for exact values, you could go for 4.5. 4.5 being a terminating decimal, we could also use that nicely as well in this case. Okay, for the next part, we're now looking at the variance. So again, highlighting that, our variance is the x squared times by our probability. So we get that as our answer, but we should also know that we're then going to take away from that answer the expected value being squared. And if we do that, we should get 27 on 20, which gives you the value of about exactly 1.35 as a decimal, or again, in expected value form. Okay, so hopefully that's helped people with that part of it. Now, I'm going to jump through. We've already done some stuff on this. I've prepared a few slides. Again, it's always good to have more than less. But again, I'll leave people, this is probably good practice if you haven't downloaded the PDF to have a go at some of the PowerPoint, to have a go at some of these other questions. I'm going to jump to the last couple of slides, so question 7 and question 8, just so that we have covered the normal distribution, which is obviously another very, very big part of all this. There are some very, very good notes features that are already available, and again, a few of them I was going to use tonight. There is a really nice notes page, which again I'll put up on the share drive that actually can work out some of these for you. There's one that works nicely with the Z scores, and one that I was playing with earlier tonight. But what I wanted to show you is just how you could graph something like this and put it together yourself as a graph. So in the new page, I'm going to go into Document. I'm going to go into Insert, Problem, and what I want to do is graph this normal distribution. So really what I want to show people with this particular question is it is possible to graph a normal distribution and use our means and standard deviations. And again, there are notes pages that are out there that does this nicely for you. But if you do want to start this from scratch, or if you want to do some stuff within the exam on this work, we can actually use this format. Now, in here, under the menu, we have got our normal, we can go through our menu settings and find our different options, but I'm actually going to just type this one in, normal PDF. We should know that fairly commonly from what we've done previously. Brackets. Now, because why we're doing a PDF here is we want to graph each individual value. They are continuous, so we want to graph the values of our distribution. X is going to be our variable. Because we're looking at a standard situation, a standard normal, I'm going to make 0 as our mean and 1 as our standard deviation. If we graph that, you'll actually notice we get a nice normal curve occurring on the screen. Now, obviously at the moment it's not appearing greatly, so what I'll do is I'm going to change my zoom window. And normally, being a standard normal, I'm going to go for -4 just to give us a little bit of more of a tail. Normally it would be -3 to 3 for our standard deviations, and then the tail would continue. Whoops. I'm going to make our scale 1 for our x-axis, and then in terms of going upwards, I'm just going to go a little bit below the y-axis, and then I'm going to go up to, let's make it 1. Let's see what that does for us. And we get our nice bell curve appearing. Now, because we want our Z score between -1 and 1, We're going to go into menu, analyse graph, and because it's continuous, we can use our integral. -1 is our lower boundary. 1 is our upper boundary. And what we should find very nicely there is, if I just drag that across, 0.683, which again should be looking fairly familiar to students in terms of our lower and upper boundaries and one standard deviation either side of our mean of 0. That gives us our z-score value for that situation, or sorry, our area for those z-scores of -1 and 1. We could do the same thing for -2 and 2, and you'd get the appropriate value for that particular area. Okay, last screen I'll just jump into is the normal distribution, which is a manufacturer of car tyres believes the life of their tyres forms a normal distribution with a mean of 40,000 and a standard deviation of 5,000 kilometres. What proportion of tyres lasts less than 35,000 kilometres? So for the last time tonight, I'm going to give people a chance to just see if they can work out maybe the first couple of these answers. So I'll just give people, again, about 30 seconds to see if they can work out Part A and Part B.
See if we get that speedy response again.
Yeah. While we're doing that, I might just have a quick drink of water, people. It's been a big night for me.
It's been a very good balance of ideas that really illustrate the key concepts, and also mixed in with the types of questions that students are likely to encounter on their exams and how to approach those exam problems, which I think has been a lovely balance, Stephen.
Thank you for that, Brian. And look, again, it's always hard. There's so much and so many things we like to get through in these nights and try to cover as many things as possible. But what I would be suggesting is there's some really, hopefully, good questions here that you can take back with your teachers and maybe spend some time with them or have a go at them and ask them. Also, next week we will hopefully have a little bit of time. The last topic will be a little bit shorter, so it might be a good opportunity if you do have any questions. I know that one of the people who I saw earlier was with us was asking about programming in one of the first sessions, and I was going to actually mention about where they could find some really good information about how to make up their own programs at this late stage of the course. And I know my own students have been very involved in trying to write notes pages, so we might allow for a little bit of time that in our last session next week. Okay, have we had any answers coming through, Brian?
We have. Brains Trust have come up with a value. Yep. Do you want to hear it?
I will go for that there, yes, and see if we can get it replicated.
0.1587.
I better write this down. 0.1587. Is that for the first one?
Yep.
And do we have any answers for Part B, Brian?
No.
No. Okay. We're keeping an eye on the time.
We do.
Whoop,
Sorry.
Whoop.
Yep. Just scrolling down on the chat window. 15 point. Yeah. Well, basically, that as a percentage, 15.87%.
Okay. Or 0.587. Okay, let's see what we get. So just to finish off this slide, and again, we'll probably just look at Part A and Part B here. What proportion of tyres last less than 35,000? We're now into a normal distribution, so the things that we should be looking at here is a manufacturer. It tells us very clearly is a normal distribution. We would expect that the mean value or the mean value of the life of these tyres should be somewhere in the middle, and it's got a nice standard deviation. So I'm going to create a new last screen, insert problem. We're going to go into calculator, in menu and probability, distributions. Now this time, because we're looking for a proportion and it's a range of values, we're looking at a normal CDF. Our lower boundary, now because it's lasts less than 35,000, I know there's been some debate in some of the textbooks over here, Brian, but some people are saying negative infinity, some are saying 0. I guess with the size of values here, the tail is going to be so insignificant by that stage, it really doesn't make a lot of difference. I guess if the mean is a little bit closer to the 0, we start having some issues. 35,000 is our upper bound. Our mean is 40,000. Now, I guess the thing to really remember here, students, is often they'll give you a variance in the question. Remember, if you get given a variance, you must square root it to get your standard deviation. In this case, they've been nice to you and given you 5,000. If we press OK, and lo and behold, Brian, our very, very smart participants out there have got the right answer for that first one. Just to finish off, I might actually jump to D. D is a little bit of a different question here. The company advertises 85% of our tyres last longer than M kilometres. What should M be? So longer than M. Okay, now the thing we need to remember here is we're now looking at a K value. So menu, probability, distribution, normal inverse, because we're looking for a K value. Now, it's saying 85% of our tyres last longer than M. We must put in a left value there, which is 0.15, our mean of 40,000, our standard deviation of 5,000, and if we do that correctly, we should get a value of 34,817.8. Again, depending on what the question asks for us in terms of our rounding, and that tells us that 15% of our tyres would last below that amount and 85% would last above that amount. And on that note, I think I've come to the end of my amount, Brian. I know, again, that we've skipped over a few things and things I would like to have covered, but I see it's 6 o'clock, so I will pass it over to you. And I know a lot of my students have a big Year 12 dinner on tonight with their different house groups. So, I know they're ready to rush off between 6 and 6:30, so I'll leave you to it, Brian. Thank you very much.
Oh, terrific, and thank you. And I think people have done well with other commitments to join the session tonight. That's fantastic, and I think they will agree that it's been well worth their while doing it. As I mentioned before, a very good summary of the key points there, and backed up by exam-style questions that the students are likely to encounter. And I also think that this topic, more than any other, is where you will have an edge if you there's a real expectation, put it this way, by the examiners that you understand how to drive the templates and features of your calculator to get into these distributions. You can see it all through there. I highly recommend that students download the PowerPoint. So this is it here. So go to the shared drive, download the PowerPoint, work through the questions again. Well done, especially for those who quickly gave us responses to these as we went along. Take your time as well. Go through the questions, take your time, nut through the results, and perhaps also refer to the YouTube clip that you will get the link to shortly, and review tonight's webinar. I think it's an absolutely terrific one. The sad thing is we're just about at the end of our course. One session remaining, and that will be next week. And it actually builds upon what we've been doing this afternoon, and that is sampling and interval estimates for proportions. So that's our last final session. And then if you've attended them all, you get a special certificate of attendance for the course. So and completion of the course. So next Monday afternoon, 5 o'clock Western Standard Time once again. We look forward to seeing you then. I bid you well and enjoy the dinners for those of you who are attending those this evening. All the best.